March 3, 1935. King's Cross Station, London. Sir Nigel Gresley stands beside a chalk-marked blackboard in the London and North Eastern Railway engineering offices, staring at a number that makes senior engineers shake their heads. In disbelief, 126 miles per hour. The room erupts in objections. Railway experts from across Britain had gathered for this design review, and none believed what Gresley was proposing. Steam locomotives had physical limits. They argued limits defined by thermodynamics, metallurgy, and a century of rail engineering experience. The fastest steam engine in history, Germany's Class 05, had barely touched 124 miles per hour under controlled conditions before mechanical failures forced abandonment of further speed attempts. British railway tradition emphasized reliability over spectacle. The Great Western Railway's chief mechanical engineer had published calculations proving that steam locomotives faced insurmountable barriers above 115 miles per hour, boiler pressure, limitations, wheel balance issues, and aerodynamic drag created conditions where attempting higher speeds would tear an engine apart from the inside out. Gresley listened to the criticism without interruption, then walked to the blackboard and drew a single curved line, the profile of something unprecedented in steam locomotive design. Not the angular, boxy shape of traditional engines, but a smooth, aerodynamic shell that enclosed the entire locomotive in a streamlined casing. The senior engineer's objections intensified. Streamlining was expensive, difficult to maintain, and provided questionable benefits at the speeds British trains actually operated. German engineers had experimented with streamlined steam locomotives, but results showed minimal performance improvements that didn't justify the added complexity and cost. Besides, they argued, the real problem wasn't aerodynamics, it was fundamental physics. Steam locomotives generated power through reciprocating pistons that drove wheels through connecting rods. At high speeds, these reciprocating masses created vibrations that increased exponentially with velocity. Above 120 miles per hour, the mechanical oscillations would overwhelm any engine's structural integrity, causing catastrophic bearing failures, cracked cylinder heads, and wheel fractures. Gresley had anticipated every objection. For 18 months, he'd been developing something radically different from traditional British locomotive practice. Not just cosmetic streamlining, but a complete reimagining of high-speed steam locomotive design that addressed every technical limitation that made 126 miles per hour seem impossible. His proposal called for innovations that veteran engineers dismissed as unnecessary complications. A revolutionary double-chimney exhaust system that improved boiler efficiency at high speeds. Precision wheel balancing techniques that minimized reciprocating mass vibrations. A boiler design that maintained steam pressure under sustained high-power operation. And most controversially, that streamlined casing that enclosed the entire locomotive in an aerodynamic shell. The London and North Eastern Railway Board faced a decision that would define British rail engineering for decades. They could follow established wisdom and abandon Gresley's high-speed ambitions, or they could approve funding for an experimental locomotive that might prove steam power still had untapped potential or might validate every expert's prediction of catastrophic failure. Young designer who proposed breaking the impossible speed barrier was about to discover whether systematic innovation could overcome a century of engineering limitations. By September 1935, construction had begun at Doncaster Works on what would become locomotive number 4468. Unlike traditional locomotive development that relied on established designs with incremental improvements, Gresley's team approached the project like an extended physics experiment. The aerodynamic shell design emerged from systematic wind tunnel testing, a methodology previously reserved for aircraft development. Gressley had commissioned tests at the National Physical Laboratory, subjecting scale models to airflow analysis that measured drag coefficients with scientific precision. Traditional locomotive designers trusted visual aesthetics and craft experience. But Gressley's team quantified air resistance forces at specific velocities. The wind tunnel data revealed counterintuitive results. At speeds above 100 miles per hour, aerodynamic drag consumed more power than mechanical friction in wheels and bearings. A conventional steam locomotive's angular profile created turbulent airflow that increased resistance exponentially with speed. The streamlined casing reduced drag by 33% at 120 miles per hour compared to standard locomotive designs, enough to make the difference between possible and impossible. But streamlining solved only one problem. The fundamental challenge remained: generating sustained power at velocities where mechanical stresses destroyed conventional locomotives. Gressley's solution centered on the Kilchap double-chimney exhaust system, a French innovation that British engineers had largely dismissed as unnecessarily complex. Traditional single-chimney locomotives created exhaust back pressure that limited boiler efficiency at high speeds. The double-chimney design split exhaust flow through two optimized pathways, improving draft through the firebox while reducing pressure resistance. Testing showed the system increased boiler efficiency by 8% at maximum power output, providing additional horsepower exactly when high-speed operation demanded it most. The wheel balancing requirements pushed British precision manufacturing to unprecedented levels. Gressley specified tolerances measured in thousandths of inches for the driving wheel's dynamic balance. Small weight imbalances that caused negligible vibration at 60 miles per hour would create destructive oscillations at 120 miles per hour, potentially shattering wheel spokes or fracturing axle bearings. DONCASTER Works installed specialized balancing equipment that German locomotive manufacturers had developed for their high-speed experiments. Each driving wheel underwent individual testing while rotating at speeds equivalent to 140 miles per hour operation, with technicians adding or removing tiny weight adjustments until vibration measurements fell within specified limits. The process took 3 times longer than conventional wheel balancing, but eliminated the mechanical oscillations that had destroyed previous high-speed attempts. Boiler design incorporated pressure vessels operating at 250 pounds per square inch higher than most British locomotives required. Sustained high-speed operation demanded continuous steam generation that conventional boilers couldn't maintain without pressure drops that reduced power output. Gressley's boiler featured enlarged fireboxes with improved combustion airflow and increased water circulation capacity that sustained steam pressure during extended maximum power operation. By early 1938, locomotive 4468 stood complete in Doncaster Works, a machine that looked fundamentally different from any steam engine British railways had operated. The streamlined casing gave it the appearance of a speeding bullet, while beneath the shell lay engineering innovations that addressed every technical barrier, preventing sustained 120 miles per hour operation. Critics remained unconvinced. The proof would come not from laboratory testing, but from actual track performance under conditions where previous locomotives had failed. Catastrophically, what made 126 miles per hour seem impossible wasn't theoretical, it was based on documented failures that had killed engineers and destroyed locomotives across Europe. The physics of high-speed steam operation created problems that increased dramatically with velocity, and every attempt to push past 120 mph had ended in mechanical disaster. The German Reichsbahn's experience with locomotive 052 provided the most comprehensive documentation of high-speed steam's limitations. In May 1936, during a controlled speed attempt on straight, level track between Hamburg and Berlin, the locomotive reached 124.5 miles per hour before engineers detected dangerous vibrations in the driving wheels. Post-run inspection revealed stress, fractures in the connecting rod bearings, and heat. Damage to cylinder lubricating systems. German engineers published detailed analysis showing that reciprocating masses, the pistons, connecting rods, and associated components created inertial forces that increased with the square of velocity. At 60 miles per hour, these forces remained within safe limits. At 120 miles per hour, they quadrupled. Above 125 miles per hour, the mechanical stresses exceeded the structural capacity of available steel alloys. British railway experts used this data to argue that Gressley's 126 miles per hour target was physically impossible. With existing materials and manufacturing techniques, the Great Western Railway's engineering department issued technical papers demonstrating that steam locomotive wheel arrangements faced absolute speed limits based on reciprocating mass calculations. Their analysis showed that even with perfect wheel balancing, speeds above 122 miles per hour would cause bearing failures within minutes of sustained operation. The aerodynamic challenges compounded mechanical limitations. Wind tunnel testing by multiple research institutions confirmed that conventional locomotives created massive turbulent wakes at high speeds. The turbulence consumed power exponentially at 100 miles per hour. Aerodynamic drag accounted for 30% of total resistance. At 120 miles per hour, it rose to 48%. At 126 miles per hour, calculations suggested drag would consume over 55% of available power output. Traditional British locomotives generated approximately 2,000 horsepower at maximum output. Calculations showed that reaching 126 miles per hour required 2,800 horsepower continuously, 400 horsepower more than conventional boilers could produce sustainably. Critics argued that Gressley's double-chimney exhaust system couldn't bridge that performance gap, particularly when mechanical friction losses increased with speed. Track condition concerns presented additional barriers. British Railways operated on infrastructure designed for trains traveling 75 to 90 miles per hour maximum. At 126 miles per hour, minor track irregularities that caused negligible disturbance at normal speeds would create violent vertical accelerations that could derail the locomotive or damage suspension components. Railway civil engineers warned that attempting such speeds without track modifications risked catastrophic derailment. The signaling system limitations added final evidence that high-speed steam operation exceeded safe boundaries. British railway signals were spaced for trains that could stop from 90 miles per hour within established braking distances. A locomotive traveling 126 miles per hour would require 50% greater stopping distance, potentially running past danger signals before engineers could react to changed signal aspects. By early 1938, the engineering consensus remained firm. Steam locomotives faced fundamental physical limits that made sustained operation above 120 miles per hour impossible with existing technology. Gressley's streamlined experiment would either validate these limits or disprove a century of accepted railway engineering principles. The morning of July 3, 1938, began with meteorological conditions that seemed designed for record attempts. Clear skies over Lincolnshire, minimal crosswinds along the East Coast Main Line, and track temperatures that kept rail expansion within optimal ranges. Locomotive 4468 Mallard stood at Barkston Junction, coupled to a dynamometer car and 6 coaches carrying railway officials, LNER engineers, and instrumentation equipment. Driver Joseph Duddington had received explicit instructions that differed from any assignment in his 28 years of railway service. Instead of maintaining scheduled speeds and conserving coal, he was authorized to operate Mallard at maximum power output for an extended period, something drivers normally avoided due to mechanical wear concerns and safety regulations. Test route stretched from Grantham to Peterborough, including a 4-mile section of 1IN 200, gradient descent near Little Bitham where gravity would assist acceleration. Gressley's team had calculated that this location provided optimal conditions for reaching maximum velocity, while maintaining safety margins for braking before speed-restricted sections. At 16:45, Mallard departed Grantham Station, accelerating through the northern suburbs with increasing urgency. Duddington opened the regulator fully, driving steam pressure to maximum ratings, while fireman Thomas Bray maintained intense firing rates to sustain boiler pressure. The double-chimney exhaust system produced its distinctive sound, not the single explosive bark of conventional locomotives, but a rapid, almost turbine-like roar as exhaust gases split through optimized pathways. Speed climbed steadily through familiar benchmarks. 80 miles per hour past Barkston, 90 miles per hour approaching Corby Glen, 100 miles per hour at Little Bitham Village. The dynamometer car's recording equipment tracked velocity with precision chronometers, creating permanent documentation of performance that would validate or refute years of engineering work. At 105 miles per hour, Mallard entered the gradient descent where gravity would provide additional acceleration. Duddington maintained maximum power rather than allowing the locomotive to coast, combining gravitational assistance with full boiler output. The streamlined casing performed exactly as wind tunnel testing predicted, slicing through air resistance that would have overwhelmed conventional locomotive profiles. Speed increased with startling rapidity. 110 miles per hour, 115 miles per hour, 120 miles per hour velocities where German engineers had detected dangerous vibrations and mechanical stress. Mallard remained stable, its precision-balanced wheels rotating at 5.3 revolutions per second, without the destructive oscillations that critics predicted. At 16:58, instruments recorded 126 miles per hour, a speed British railway experts had calculated was impossible for steam locomotives to achieve safely. Duddington maintained that velocity for approximately 300 yards before beginning deceleration. Concerned about approaching speed restrictions and the intense mechanical demands of sustained maximum operation, the dynamometer recording showed something remarkable beyond the headline speed figure. During the high-speed section, boiler pressure remained steady at 245 pounds per square inch, demonstrating that the enhanced boiler design sustained steam generation under conditions that would have exhausted conventional systems. Wheel bearing temperatures stayed within acceptable ranges despite operating speeds that should have caused catastrophic friction. Heating. Mallard had accomplished what engineering consensus declared impossible, not through luck or reckless operation, but through systematic application of aerodynamics, thermodynamics, and precision manufacturing that overcame every technical barrier critics had identified. The dynamometer car contained equipment that eliminated any possibility of measurement error or exaggerated claims. Unlike previous speed record attempts that relied on trackside timing or driver estimates, Mallard's run produced continuous mechanical recordings calibrated to scientific standards. The primary instrument, a Flamen speed recorder, used a mechanical connection to the locomotive's wheels that traced velocity measurements onto a paper chart through a stylus arm. The resulting graph showed acceleration rates, maximum speed, and deceleration patterns with precision that couldn't be disputed or adjusted after the fact. Railway engineers worldwide recognized Flamen instruments as the definitive standard for locomotive performance measurement. The chart recorded a peak Velocity of 126 miles per hour. Sustained for approximately 7 seconds at maximum, with nearby measurements showing 125.5 miles per hour, maintained for over 300 yards of track. The gradual acceleration curve demonstrated this wasn't momentary wheel slip or measurement anomaly, but genuine sustained high-speed operation. Secondary verification came from timing measurements taken by railway officials, using precision stopwatches synchronized to railway telegraph time signals. Multiple observers timed Mallard's passage between established milepost markers, calculating speeds that corresponded within 1% of the dynamometer recordings. The redundant measurement systems eliminated any suggestion of instrumentation failure or recording error. Post-run mechanical inspection revealed the physical evidence of extreme operation. Driving wheel bearings showed temperature indicators consistent with sustained high-speed rotation, but remained within design tolerance ranges. The middle big end bearing connecting the piston rod to driving wheel had run hot enough to partially melt its white metal bearing surface, requiring immediate replacement. This damage confirmed that Mallard had operated at the absolute limits of mechanical capacity, but also proved that Gressley's engineering calculations had accurately predicted failure modes and provided sufficient safety margins. The bearing damage actually strengthened credibility rather than undermining it. Critics couldn't claim Mallard had been operated conservatively or achieved its speed through measurement error. The physical evidence showed the locomotive had been pushed to its mechanical limits. Yet despite reaching that extreme condition, the essential structural components remained intact and operational. Most significantly, the wheel balance precision Gressley demanded proved its worth. Detailed vibration analysis of the driving wheels post-run showed they remained within specified dynamic balance tolerances despite operating at speeds that had destroyed wheels on previous high-speed attempts. The precision manufacturing that skeptics dismissed as unnecessary expense had been essential to preventing catastrophic mechanical failure. The boiler pressure charts demonstrated sustained steam generation that conventional locomotives couldn't match. Throughout the high-speed section, pressure remained above 240 pounds per square inch despite maximum power output, confirming that the double chimney exhaust system and enhanced boiler design delivered the performance advantages Gressley predicted within 48 hours. Technical journals published detailed analysis of the dynamometer recordings. The Institution of Mechanical Engineers validated the measurements as scientifically rigorous. German railway engineers, whose own high-speed experiments had established previous records, acknowledged Mallard's achievement as legitimate and unprecedented. The locomotive that experts said couldn't safely exceed 120 miles per hour had not only reached 126 miles per hour but had done so with documented evidence that eliminated any possibility of dispute, establishing a steam locomotive speed record that would never be broken. Mallard's 126 miles per hour record, set in 1938, remains unbroken not because later engineers lacked ambition, but because the conditions that made the attempt possible disappeared permanently within a decade. By 1948, British Railways nationalized all railway companies, consolidating operations under a single entity focused on operational efficiency rather than prestige engineering achievements. The new management prioritized standardization and cost reduction over experimental high-performance locomotives, resources that might have funded further speed record attempts went instead toward rebuilding war-damaged infrastructure and developing diesel-electric locomotives that offered better operational economics than steam power. The immediate post-war period saw rapid advancement in diesel and electric traction technology that made high-speed steam development obsolete before anyone attempted to surpass Mallard's record. By 1955, French electric locomotives were routinely operating above 150 miles per hour on electrified routes, demonstrating that the future of high-speed rail lay with electric traction rather than steam power improvements. More fundamentally, Mallard represented the absolute pinnacle of what steam locomotive technology could achieve within physical constraints that couldn't be overcome through further engineering refinement. The middle big end bearing failure during the record run revealed that sustained operation above 125 miles per hour exceeded the mechanical limits of reciprocating steam design. Additional power output wouldn't solve problems created by reciprocating mass inertia. It would simply cause failures in other components. German engineers reached similar conclusions after analyzing Mallard's achievement. Theoretical studies showed that reaching 130 mph would require either exotic materials that weren't economically viable for locomotive construction or fundamental redesign of steam locomotive architecture that would sacrifice the reliability advantages of proven reciprocating designs. The streamlining techniques that enabled Mallard's record run became standard practice for post-war diesel and electric locomotives. But those designs eliminated the reciprocating mass limitations that constrained steam power. Electric motors provided smooth rotational power without the vibration-inducing pistons and connecting rods that limited steam locomotives' maximum safe speeds.